Our consideration of conformations of cyclohexanes continues with the case of substituted cyclohexanes. That is, when one of the hydrogens is replaced with something else. We will start by considering monosubstituted cyclohexanes. If you have one substituent, would that substituent prefer to be axial or equatorial? In other words, which case would be lower in energy? Well, the answer is equatorial. And that may not be intuitively obvious to you, but in reality, substituents in equatorial positions have the least steric crowding. In an axial position, it may appear that this CH3 for methyl cyclohexane is out of the way of everything else because it's outside of the main plane of the molecule, so to speak. But realistically, it's not out of the way of everything else. What it is close to are the hydrogens 2 carbons away. You see that? I can bend my model just a little bit and knock the CH3 into either of those hydrogens. If we look at a Newman projection for an axial position on the right here, the CH3 group can bump into one of the hydrogens going down 2 carbons away, carbon 1, carbon 2, carbon 3. If we do a ring flip and put this methyl group equatorial, it really does get out of the way of everything else. There is nothing I could do to bend or rotate this CH3 that will bring it close enough to anything else to potentially cause a problem. Okay, so the equatorial positions are off to the side. The type of steric crowding involved when we have an axial substituent, we have a special name for it, and it is called a 1,3 diaxial interaction, because as we said, the substituent at C1 is too close to the CH2 or the hydrogen at carbon 3. And when we look at the Newman projection of a 1,3 diaxial interaction, you can see that this interaction is similar to a gauche interaction in an acyclic molecule. Okay, and just like gauche interactions, just like gauche conformations that have gauche interactions are higher in energy than anti-conformations for butane, the 1,3 diaxial interaction causes some steric crowding also in the cyclohexane that is usually enough to cause the substituent to prefer to be equatorial. So how much the substituent prefers to be equatorial actually depends on the size of the substituents. Okay, the amount of steric crowding is proportional to the size of a substituent. So for methyl cyclohexane, the energy difference between the equatorial and the axial conformations is 7 kilojoules per mole, and if you plug that into your delta G equals minus RT ln K equation, you will get that methyl cyclohexane is equatorial 95% of the time, or if you prefer, that 95% of the methyl cyclohexane molecules are equatorial. If we go larger than methyl, if we go to terp-butyl cyclohexane, the energy difference is now 21 kilojoules per mole. It is 3 times as big, and therefore terp-butyl cyclohexane is 99.99% equatorial. At that point, we say that it is completely equatorial, or that it is locked in the equatorial conformation, because we cannot detect any of the axial conformation. If you have a 95-5 mixture, usually using sophisticated techniques, you can detect a minor component of a mixture if it's 5%, but not if it's only 0.01% of the mixture. Okay, so that's our conclusion that with monosubstituted cyclohexanes, substituents would rather be in the equatorial position. Now, what about disubstituted cycloalkanes, when you have two substituents? Well, this is going to bring us into a case where we have cis and trans isomers. Cis and trans isomers are a concept that you've already met in the context of alkenes. If you have two substituents on an alkene, if they're on the same side of the double bond, it's cis, and if they're on opposite sides of the double bond, it's trans. Well, for rings, it works exactly the same way. Two substituents are cis if they're on the same side of the ring, and trans if they're on opposite sides. In fact, you can think about an alkene as being a two-membered ring. That may not work for everybody, but if it works for you, it helps you put this into perspective with the terminology that you've already learned in a different context. So we'll look at a five-membered ring as an example. So you can have two different groups. If they're on the same side, they're going to be cis, and this should be 1,3-dimethyl cyclopentane. And if they are on opposite sides, they are going to be trans. Again, when we draw this, we typically draw it looking at it from the top. So something coming towards you is going to get a wedge. Something going away from you is going to get dashes. In this case, both of the balls are coming towards you in the cis, so they're both going to get wedges. Okay, so for cyclohexanes, even though they're not planar, it's sometimes convenient to draw them planar in order to demonstrate the relative orientations of the substituents, namely that of up versus down. And being able to translate a planar drawing into a proper chair drawing and vice versa is an essential skill. The cyclohexane is not ever going to be planar, but trans 1,2-dimethyl cyclohexane will sometimes be drawn with a planar hexagon, and then we will have one substituent with a wedge and another substituent with a dash. Well, what does that mean? The one with the wedge is pointing up, or up above the mean plane of the molecule if you looked at it from above. The one with the dash is pointing down. Now, we already know that equatorial is favored more than axial is. So in the case of 1,2-dimethyl cyclohexane, we can have both substituents occupy equatorial positions. One of them is pointing up and out, and the other one is pointing down and out. In the case of cis 1,2-dimethyl cyclohexane, you cannot have both of them equatorial, because if they're both going to be up, one of them can be equatorial, but then the other one has to be axial. So cis 1,2 has one axial, one equatorial. Trans 1,2 can, in theory, have both axial or both equatorial, but as you now know, it's going to want to adopt the conformation where both of them are equatorial. Now, what about 1,3? If you have a cis 1,3 where both of these substituents are pointing up, they can both be axial or both be equatorial. Once again, the molecule is going to do a ring flip and adopt the conformation where both of them are equatorial. Trans 1,3, where one is up and one is down, you're going to have one equatorial and one axial. The 1,4 relationship then turns out to be the same as the 1,2 relationship. If they are cis, in other words, if they are both up, one of them can be equatorial, but then the other one has to be axial. Whereas if they are trans, so this one over here pointing up, that one on your left pointing down, the trans 1,4 can have both of them equatorial. Once again, you can have a trans 1,4 where both of them are axial, but that's not going to be the stable conformation. It's going to undergo a ring flip to move both of them equatorial. Okay, one of the problems that you will have to solve involving this material is determining what the lowest energy conformation is given two possible structures. Okay, recall that a ring flip turns axial positions into equatorial positions and vice versa, so the lowest energy conformation is the one that has either the largest group equatorial or the greatest number of groups equatorial. And we'll look at a couple of examples of this. Okay, this is the case of a trans 1,2 dimethyl cyclohexane. So the question is, which of these conformations is going to be lower in energy, the one with both of them axial or the one with both of them equatorial? And from the discussion we've had already, you should be able to realize that the lower energy conformation has both of them equatorial. In this case, we've got a cis 1,2 in which we have a methyl group and an isopropyl group. Okay, what are our two possibilities if we redraw them in their proper chair conformation? If it is cis 1,2, you're going to have one axial and one equatorial. So we can either have the isopropyl group equatorial and the methyl group axial, or the isopropyl group axial and the methyl group equatorial. Well, an isopropyl group is larger than a methyl group, therefore it's going to want to adopt the equatorial position and force the methyl group into the axial position. Therefore, the lowest energy conformation is the one on the left over here. Another good thing to do to practice with this topic is to be able to go back and forth between a planar drawing of a cyclohexane and the proper chair conformation. In fact, it's worth your while spending some time just drawing proper chair conformations, because the better your drawing is, the more faithfully it will represent what's actually happening in the molecule and make it easier for you to see the relative orientations of two groups. If your axials are really and truly pointing straight up or straight down, and your equatorials really are pointing up and out or down and out as they need to be.